How's it going, guys? Today we're going to go over another interview question on LeetCode. Today we're going to review a problem from Amazon, and today our problem is called Subtree of another tree.
Today's agenda, got the suitcase up in the center. Go to room 112, tell them Blanco sent you. Feel the strangers, if no money exchanges. I got this kid.
Alright guys, today before we start our video, I just want to thank today's sponsor, Rooftop Slushy. Rooftop Slushy is a product that offers an entire suite of services to ensure that you're ready for your FANG interviews. One of my favorite things that they offer actually is their job interview section. This section allows you to view questions that other applicants have asked in the past about their respective interview processes at FANG, as well as view answers that were given to that applicant by FANG engineers themselves. Sometimes all you need to succeed is just that little bit of advice from the inside, and I definitely think Rooftop Slushy gives you just that. If you guys are interested in checking out Rooftop Slushy, be sure to check the link in my description. It'll give you 10% off your first purchase for a service like a resume review or even a direct referral to FANG. Alright guys, so today the problem's from Amazon. It's Subtree of another tree. LeetCode says it's easy, but I'm not totally convinced. As always, and our problem description says, given two non-empty binary trees S and T, check whether tree T has exactly the same structure and nodes values with a subtree of S. A subtree of S is a tree that consists of a node in S and all of its nodes' descendants. The tree S could also be considered as a subtree of itself. Okay, so really all we're asked is that we're given some tree S and some tree T, and we want to know if this tree T exists somewhere entirely in this tree S. So if we were given these different examples now, we're going to basically walk through them quickly and know whether or not they would return true or false. So if we look at the first example here, right, if our tree S was this tree here and tree T was this tree here, we'd actually return true, right? Because we can see that this tree here, the entire tree T actually occurs as a subtree in our tree S here, right? So 4, 1, 2. So it entirely occurs, right? The entire tree T occurs inside of S. So we'd return true that it is a subtree of this other tree. So now looking at example 2, if we were given this tree S and this tree T, we'd have to return false, right? And it kind of looks like we would return true, right? Because we can see that this entire subtree actually appears here. But the problem tells us, if we scroll back above, that a subtree of S is a tree consisting of a node in S and all of its nodes' descendants, right? So because we have to consider all the descendants of 4, that includes this 0. And so because of that, we can't say that this entire tree, right, 4, 1, 2, and 0 are exactly the same as this subtree T. So because we can't actually exclude this 0 here, we have to say that it's false. We have not found the exact same entire subtree T inside of S when we have to consider that 0. All right, so I want to try something different here. So today I want to talk through the examples on my iPad a little bit, just talk about how we're going to try and solve this problem. So here we have the first example that we were given in the problem. And what we really want to do is we want to check if this subtree, right, occurs inside of this tree. So if T occurs inside of S. So what we really want to do is we want to ask, is this node the same as this node? And if it is, we want to continue traversing to these children, right? So if it is, we want to keep going to this child and this child. So effectively what we're really going to do is we're going to take this entire subtree, or this entire tree really, and try and place it on top of this tree. And here we would see that, okay, the first two squares that I just drew are not the same trees, right? Very clearly they're not. So what we're going to do is we're going to traverse to the children of the node we just checked. So we traverse to 4 and then try and do the exact same thing. Continuously compare all the nodes' values to see if they look the same, and they do, right? So this subtree does look exactly like this subtree, so we return true. So now if we look at example 2 here, right, if we have this tree T and this tree S, we want to try and do the same thing, right? So we really want to take this tree and try and overlay it onto all the different trees or subtrees that are in S, right? So we'd start from the first level and we try and do this effectively. We try and overlay this. So the first check we would do is see if this node, if its value matches this node, and it does not, right? So then that means that we need to try and redraw this box at different levels of S, right? So this level did not match, so now we're going to go to the next level. So now we're going to check this, and we're going to check whatever this would be, right? But this really doesn't have subtrees, so we don't have to keep traversing. But regardless, we'd get to this level and we check if 5 is equal to 4, and it's not, so we'd stop, right? And then we'd also check this subtree now, and what we'd do is we'd see that, okay, they seem to all check out, but then once we get down to this last level, right, they don't match. So therefore we'd end up returning false. So we really want to take our smaller tree, or really, I guess not necessarily smaller, but our tree T, and try and just overlay it onto our tree S at every single level. So we're going to see if the nodes match at first. If they do, we'll continue traversing and check that all the subsequent nodes match. And if they don't, we're just going to ask the exact same question, but restart from lower subtrees inside of T. So hopefully that makes a little bit more sense now, and now I just want to start writing the code in our editor. So the first check I really want to have is just if our tree S is null, then there's no way that our tree T can be a subtree of that null node, right? There's nothing there, it can't be a subtree. So if S is null, I'm simply going to return false because T can't possibly be a subtree of null. Otherwise, we want to do what we talked about on the iPad, right? We basically want to ask, for the level that we're on, does the entire tree T appear in the entire subtree of S? So I'm going to say else if, and we're going to write a magical recursive function like we always do. If they are the same tree, S and T, we're going to end up returning true. And otherwise, right, we're going to do what we said again on the iPad is if the two nodes, if we can't find the subtree T inside of S at the current level that we're on, we're going to move to the next level and ask the same question, right? So I'll say else, we want to return if there is a subtree between S.left and T, or if there's a subtree that matches, so is subtree inside of S's right subtree with the entire tree of T. Great. So now all that we have to do here is just write our magical recursive function, right? So we called it, it's going to return a Boolean, right? Whether or not those two trees are the same trees. We're going to say public Boolean is same tree. We took a tree node S and a tree node T. And now we just basically need to traverse the entirety of each of those subtrees, right, that we passed here on line 14 and check if they are the same. So the first easy check to have is if either of them are null, we need to make sure that they are both null, right? We can't have one have a value and one not have a value, because then that would mean that they're not the same tree. So we can simply check if S is null or T is null. So if either of them are null, they have to both be null. So I'll just return if S is equal to null and T is equal to null. Great. Now otherwise, if they are not null, right, we have two nodes values, definitely. We have two nodes that are not null on line 24, right? So if they're both not null, now we just need to check if they have the same value. And if they do have the same value, we need to continue our recursion to make sure that any of the descendants of our current node also match. So I'll say else if s.val is equal to t.val. We just want to continue our recursion, right? So I'll return the result of is same tree of s.left and t.left and is same tree of s.right and t.right. Because again, we need to make sure that if the current node's values are the same, the entire left subtree has to be the same and the entire right subtree has to be the same. And otherwise, right, if we have two nodes but their values do not match, then we want to return false so that we would return back to one of these calls that was made on line 14. That will not return true, right? That would return false. And then we would then ask the exact same question again, but we would be moving down the level in S. So again, we're going to try and find if T occurs inside S at the top level. If it does not, we're going to continue traversing down the different levels and the different nodes of S until we've either traversed the entire tree or we've actually found that the subtree T does occur inside of S somewhere. Okay, so now before we submit this, I just want to talk quickly about our runtime and our space complexity. So we said, on the iPad, and kind of hopefully this code, you can see it now more, but what we're doing basically is we're traversing every single node in S, right, looking for the entire subtree T. So because of that, we'd say that the runtime is O of M times N, right? So M would be something like the number of nodes in S, and N would be the number of nodes in T. And again, that's because for every single node in S, we're going to make M comparisons at max, right? Or we have to look for the entire tree T for each of those nodes in S. So now for our space complexity is going to be the minimum between M and N. And the reason for that is because if M is the number of nodes that we have in S and N is the number of nodes that we have in T, The limiting factor of how deep our recursion goes is going to be whichever tree has less nodes. So because of that, we'd say that our space complexity is the minimum between M and N, which again are the number of nodes in S and T. So now let's run this code. Let's make sure that it works. Awesome, it does. All right, guys, so that's how to solve subtree of another tree in Java. If you guys are interested in checking out Rooftop Slushy, be sure to use the link in my description for 10% off your first purchase. If you guys enjoyed this video and found it helpful, do me a favor, leave a like and subscribe to the channel for more. And I'll see you guys in the next one.
Today's agenda, got the suitcase up in the center. Go to room 112, tell them Blanco sent you. Feel the strangers, if no money exchanges. I got these kids in ranges to leave them niggas brainless. All they told is stainless, you just remain as calm as possible. Make the deal go through, if not, here's 12 shots. We know